Imagine drawing a perfectly straight line that goes on forever in both directions. Now, pick one spot and call it 0. Every single point on this line, no matter how tiny the distance, is a number. If you go to the right, the numbers get bigger, 1, 2, 3, and so on. Go left, and you get the negatives, -1, -2. But here is the key idea: there are absolutely no empty spaces. Between any 2 points, no matter how close, there is always another number. This line is completely filled, like an unbroken thread. We call this the real number line, and it is the home of every number you can think of: whole numbers, fractions, and even numbers that cannot be written as fractions. Why do we care about this line? Because it turns numbers from abstract symbols into something you can see and touch. Every number gets a physical address, a precise spot. This lets us do something powerful: we can zoom in forever. Imagine looking at the line with a magnifying glass. You see the whole numbers, then the halves, then the tenths, then the hundredths. No matter how much you zoom, the line is still solid. This and no gaps property is called completeness, and it is the secret ingredient that makes calculus work. When we talk about a limit, a number we get closer and closer to, we need to know that the number we are aiming for actually exists on the line. Without completeness, a limit might point to a hole, and the whole idea of approaching would break down. It also connects the shapes of geometry, like the diagonal of a square, to the numbers of algebra. So how is this line built? We start with the numbers that can be written as a fraction, like 1/2 or 3/4. These are called rational numbers. The word rational comes from a ratio, meaning a fraction. If you plot all the rational numbers, they are packed incredibly densely. Between any two rationals, you can always find another one, just take their average. But here is a surprise: even with all those rationals, the line still has holes. Think of a square that is 1 unit wide and 1 unit tall. Its diagonal has a length of the square root of 2. The ancient Greeks discovered, to their shock, that this number cannot be written as a fraction. It is an irrational number. Numbers like pi and the square root of 2 fill in the tiny gaps the rationals leave behind. Together, the rationals and irrationals form the real numbers, and they fill the line completely. Every single point is accounted for. Let's see why this matters with a real problem. Imagine you drop a ball from a height of 5 meters. Its height above the ground changes smoothly over time. If you plot time on the horizontal axis and height on the vertical, you get a beautiful, unbroken curve. This curve is continuous because the real numbers are continuous. At every single instant of time, there is a real number telling you the exact height. There are no jumps or gaps. Now, in calculus, we want to find the ball's speed at a precise moment, like exactly 1 second after you drop it. To do that, we look at the height over a tiny time interval and shrink that interval toward 0. This process of taking a limit only works because the real number line has no holes. The speed we are approaching is a real number that actually exists. So, the completeness of the real line is what lets us define an instantaneous speed. You already know the real number line. It's the long, unbroken ruler where every point is a number. Some of those points are rational numbers, meaning they can be written as one integer divided by another, like 3/4. Integers themselves are the easiest, they're just whole steps along the line, like -2, 0, or 5. But rational numbers have two clever disguises. A decimal that stops, like 0.75, is secretly the fraction 3/4. And a decimal that repeats forever, like 0.3 repeating, is also a fraction, 1/3. They look different, but they're all the same family, numbers that can be written as a ratio of two integers. In calculus, we chase exact answers, limits, derivatives, and integrals all demand precision. If you round a repeating decimal like 0.6 repeating to 0.67, you introduce a tiny error that can grow and throw off your whole calculation. But if you know it's exactly 2/3, you can work with it perfectly. The trick is that every repeating decimal is a rational number in disguise, and we can use a simple algebraic trick to reveal its true fraction form. This matters because the real number line is dense. Between any two rationals there's another rational, and being able to switch between decimal and fraction lets you pick the form that makes your calculus problem easiest. Here's the algebraic trick. Suppose you have the repeating decimal 0.1212 repeating, the block 12 goes on forever. First, give it a name, let x equal that number. The repeating block has 2 digits, so multiply x by 100 to shift the decimal point 2 places. Now you have 100x equals 12.1212 repeating. Look closely, the decimal parts of x and 100x are identical, they both end in the same infinite string of 1, 2. Subtract the first equation from the second, 100x minus x equals 12.1212 repeating minus 0.1212 repeating. The infinite tails cancel perfectly, leaving 99x equals 12. So x equals 12 over 99, which simplifies to 4 over 33. The repeating decimal was a fraction all along. Let's use this trick on a decimal you'll see often in calculus, 0.16 repeating, where only the 6 repeats. Set x equal to 0.16 repeating. The repeating block is just 1 digit, so multiply by 10 to get 10x equals 1.6 repeating. Now subtract the original x, 10x minus x equals 1.6 repeating minus 0.16 repeating. The infinite 6's cancel, leaving 9x equals 1.5. So x equals 1.5 over 9. Multiply top and bottom by 2 to clear the decimal, and you get 3 over 18, which simplifies to 1/6. So 0.16 repeating is exactly 1/6. This same method works for any repeating decimal. It's a reliable tool for your calculus toolkit. We already know the rational numbers, every fraction, every terminating or repeating decimal. But there are numbers on the real number line that are not rational. We call them irrational numbers. An irrational number is simply a number that cannot be written as one integer divided by another. No fraction works. If you try to write it as a decimal, the digits go on forever without ever settling into a repeating pattern. You already know some famous ones, the square root of 2, the number pi, and Euler's number e. They live on the same number line, right in between the rationals. Why do we even need irrational numbers? Imagine the real number line with only rational numbers on it. You might think fractions are packed densely, and they are. Between any two fractions there's another. But surprisingly, they still leave holes. For example, draw a square of side length 1. Its diagonal has a length, we can measure it. But that length, the square root of 2, is not a fraction. If our number line had only rationals, that point simply wouldn't exist. The line would be full of invisible gaps. Irrational numbers are the glue that fills every single gap, making the line truly continuous, what mathematicians call complete. Without them, calculus itself cannot stand, because limits would fall into those holes. How do we know for sure that the square root of 2 is irrational? We can prove it by contradiction. Start by imagining the opposite. Suppose root 2 is a fraction a over b, written in lowest terms, meaning a and b have no common factors. Square both sides to get a squared equals 2b squared. That means a squared is even, which forces a itself to be even. Say a equals 2k, plug that back in, for k squared equals 2b squared, so b squared equals 2k squared. Now b squared is even, so b is even too. But wait, we just proved both a and b are even, so they share a factor of 2. That contradicts our starting assumption that the fraction was in lowest terms. The only escape is that our original assumption was false. Root 2 cannot be written as a fraction. This elegant argument is over 2,000 years old. Let's see this in a real situation. Suppose you have a square garden, 2 meters on each side. You want to run a diagonal path from one corner to the opposite. The length of that path is the square root of 8, 2 times root 2, which is about 2.828 meters. No matter how fine your ruler, you can never mark that exact length as a fraction of a meter. It's not 2828 over 1000 exactly, the decimal never ends and never repeats. Yet the path exists, you can walk it. Irrational numbers like root 2 appear whenever we deal with diagonals, and pi appears in every single circle, the ratio of circumference to diameter. They are not rare oddities, they are the silent majority of the real number line, making our world geometrically complete. Imagine you have a handful of numbers to add or multiply. The order you combine them shouldn't change the final answer, right? The commutative, associative, and distributive properties are the official permission slips that let you rearrange numbers in an expression. They work for addition and multiplication of any real numbers, whether they're integers, rationals, or irrationals. Think of them as the basic rules of a game. Once you know the rules, you can play freely, moving pieces around to make a problem easier. Commutative means you can swap the order. Associative means you can regroup with parentheses. Distributive connects multiplication and addition, like spreading a factor across a sum. In calculus, you'll constantly face messy expressions inside limits and derivatives. Before you can apply any fancy calculus rule, you often need to clean up the algebra. These properties are your cleaning tools. They let you group like terms, reorder factors, or expand products so you can cancel things out. For example, when finding a derivative from first principles, you might need to expand something like x plus h squared. The distributive property lets you turn that into x squared plus 2xh plus h squared, which then lets you simplify the difference quotient. Without these rules, you'd be stuck. They are not abstract ideas, they are the practical levers you pull to make a problem solvable. Let's see where these rules come from using simple numbers. Picture a number line. Commutative property for addition: if you start at 0, walk 3 steps forward, then 5 steps forward, you end up at 8. If you walk 5 steps first, then 3, you still end up at 8. The total distance covered is the same. For multiplication, think of a rectangle's area. A rectangle 3 units wide and 5 units tall has the same area as one 5 wide and 3 tall, 15 square units. The associative property is about grouping. If you add 2, 3, and 4, you can add the 2 and 3 first to get 5, then add 4 to get 9. Or you can add 3 and 4 first to get 7, then add 2 to get 9. The parentheses just tell you which pair to combine first, the total sum doesn't care. The distributive property connects the two operations. Imagine you have 5 bags, each containing 2 apples and 3 oranges. Let's use these rules to simplify a limit you'll see early in calculus, the limit as h goes to 0 of x plus h squared minus x squared, all over h. First, we need to expand x plus h squared. That means x plus h times x plus h. Using the distributive property twice, we multiply x by both terms in the second parenthesis to get x squared plus xh, then multiply h by both terms to get hx plus h squared. Now we have 4 terms x squared plus xh plus hx plus h squared. By the commutative property of multiplication, xh and hx are the same, so we can rewrite them both as xh. Then we use the associative property of addition to group them x squared plus the quantity xh plus h squared, which is x squared plus 2xh plus h squared. Now plug this back into our limit. Imagine you are standing on the real number line at 0. The absolute value of any number is simply how far away that number is from you, ignoring whether it's to the left or the right. Distance is always a positive amount or 0, so absolute value is never negative. We write it with two vertical bars around the number, like x. For example, both 5 and -5 are 5 steps away from 0, so their absolute value is 5. Absolute value isn't just about 0. It gives us a ruler to measure the gap between any 2 points on the number line. If you want the distance from a number x to a fixed point a, you write x, a. This is the core idea behind the epsilon delta definition of limits in calculus, where we say x is close to a by bounding this distance. It turns a fuzzy idea of closeness into a precise number we can work with. Let's see how this distance idea solves an inequality. Suppose we want all numbers x whose distance from 3 is less than 2. We write x, 3 less than 2. This means x is at most 2 steps away from 3 on either side. To find those numbers, we think, if the distance is less than 2, then x, 3 must be between -2 and 2. That gives us two simple inequalities x, 3 minus 2 and x, 3 less than 2. Solving both, we get x1 and x less than 5. The solution is all numbers between 1 and 5, not including the endpoints. On the number line, we shade that whole interval. Imagine a factory packing bags of flour. Each bag should weigh 500 grams, but the machine isn't perfect. The quality control rule says the weight can be off by at most 10 grams. We can write this as weight, 500 at most 10. This is exactly the distance from the ideal weight. To find the acceptable weights, we split it, weight, 500 at least -10 and weight, 500 at most 10. Adding 500 to all parts gives weight at least 490 and weight at most 510. So any bag between 490 and 510 grams passes inspection. This is the same epsilon delta thinking. We set a tolerance, epsilon, around a target value. Imagine the real number line stretching out forever. An interval is simply a continuous chunk of that line, a segment with a start and an end. The key question is, do we include the very endpoints of that chunk, or do we stop just before them? If we exclude the endpoints, we call it an open interval and write it with round brackets, like a, b. If we include them, it's a closed interval, written with square brackets, the values shown here. And we can mix and match to get half-open intervals like a, b, or a, b. Think of it like a rope bridge. An open interval means you can stand anywhere on the bridge but not on the posts at the ends. A closed interval lets you stand on the posts too. Why do we care so much about whether endpoints are in or out? Because calculus is all about getting infinitely close to a point, a limit. To talk about approaching a number, we need a fuzzy zone around it, a tiny neighborhood where we can look at what a function is doing. Crucially, when we approach a point, we don't care about the value exactly at that point, only the values around it. An open interval gives us exactly that, a zone that surrounds a point but excludes the point itself. This is the seed of the epsilon delta definition. An open interval around a point C is its neighborhood, a safe space where we can study the approach without stepping right on C. Let's build these intervals from something we already know, distance. Remember, the absolute value of x minus c is the distance from x to c. An open interval around C with radius r is all points whose distance to C is strictly less than r. That's the inequality x, C less than r. This gives us C, R, C plus R, without the endpoints. A closed interval includes points at exactly distance r, so it's x, c at most r, giving the values shown here. A half-open interval just mixes the conditions. For example, c plus r means the distance from c is between 0 and r, including 0 but not r. So every interval is just a statement about distance from a center. You're setting up a ladder. For safety, the angle with the ground should be between 60 and 80 degrees. The ladder is 5 meters long. How far can the base be from the wall? The distance from the wall is the ladder's length times the cosine of the angle. The cosine of 80 degrees is about 0.17, and the cosine of 60 degrees is exactly 0.5. So the distance ranges from 5 times 0.17, which is 0.85 meters, to 5 times 0.5, which is 2.5 meters. But safety rules say the angle must be strictly between, not exactly at, 60 or 80 degrees. So the distance must be strictly between 0.85 and 2.5 meters. That's an open interval, 0.85, 2.5. The endpoints are excluded because they represent the exact danger angles. The same method solves any range problem. Find the function, plug in the bounds, and decide if the ends count. An exponent tells you how many times to multiply a number by itself. So 2 to the power 3 means 2 times 2 times 2, which is 8. A radical is the opposite idea. It asks, what number multiplied by itself a certain number of times gives me this? For example, the cube root of 8 is 2, because 2 cubed is 8. When you see a fractional exponent like a to the m over n, it combines both ideas. The denominator n means take the nth root, and the numerator m means raise that result to the mth power. So it's a compact way to write a root and a power together. Exponents aren't just abstract symbols, they describe real things. The area of a square is side length squared, the volume of a cube is side length cubed. In calculus, we constantly take derivatives of power functions like x squared or x to the 2/3. The derivative rule for powers works beautifully when the exponent is any real number, but to use it on something like the cube root of x squared, you first need to rewrite it as x to the 2/3. That's why mastering fractional exponents and radicals now is like sharpening your tools before building a house. It makes every derivative in this course feel natural. The rules come from the meaning of repeated multiplication. If you multiply x to the a by x to the b, you have a total of a plus b copies of x multiplied together, so you add the exponents. If you take x to the a and raise that whole thing to the b, you're multiplying a groups of x, b times, that's a times b copies of x, so you multiply the exponents. A negative exponent like x to the minus a means the reciprocal, 1 over x to the a. It's just a handy notation that keeps the rules consistent. For a fractional exponent like x to the m over n, the denominator n tells you to take the nth root, the number that, multiplied by itself n times, gives x, and the numerator m tells you to raise that root to the mth power. The order doesn't matter, you can take the root first then the power, or the power first then the root. Let's simplify 8x cubed, all raised to the 2/3 power. This is exactly the kind of expression you'll meet in calculus when taking derivatives. First, use the power of a product rule. The exponent 2/3 applies to both the 8 and the x cubed. So we get 8 to the 2/3 times x cubed to the 2/3. Now 8 to the 2/3, the denominator 3 means take the cube root of 8, which is 2, because 2 times 2 times 2 is 8. Then the numerator 2 means square that result, giving 4. For the x part, x cubed to the 2/3, multiply the exponents, 3 times 2/3 is 2, so we get x squared. The whole expression simplifies to 4x squared. Notice how clean that is. The fractional exponent turned a root and a power into a simple polynomial, ready for a derivative. The same method works for any similar expression you'll face in this course.